Hi class, today we're going to be discussing electrolytes and non-electrolytes. This has to do with chapter 9.2. You may have heard the term electrolytes from Gatorade commercials. They're always selling, if you do tough sports or a marathon, to drink their Gatorade because it refills your electrolytes and so forth. Let's break down what electrolytes are. And there's three different types: strong, weak, and non. So the strong is, we start out with an ionic compound. You can see ionic compounds are solid at room temperature. So if we add that to water, it will this sodium chloride will 100% completely disassociate. The water will surround them through hydration, which is what we learned in 9.1. So the ions cannot come back together and create a solid. In this case, so we start out with a solid. It comes into contact with water. It is now ions in aqueous solution. So if we look at this picture here is salt. It's sodium chloride solution. And if we have electrodes, so these little wires coming down are electrodes. And the one is a negative and the other is a positive. And the ions will be attracted to the opposite of what their charge is. And that will allow a very bright light to come through. It will be able to conduct electricity. So this light will be able to shine very, very brightly. We actually do this in lab in Chem 103. I do this. You guys can't do this. But, or Dr. Kimbrough would have shown you guys this semester. So strong electrolytes dissociate 100% in the presence of water, and it is able to produce a strong electric current, enough to light a light bulb very brightly. A weak electrolyte, the light bulb will still be lit, but it's very, very dim. And that's because you're dealing with a weak electrolyte, which means they do not disassociate 100%. In fact, acetic acid is a weak electrolyte, and it disassociates about 1%, and 99% stays intact as the molecule, which in this case, you see we have HF, and it disassociates, but it disassociates a very small amount. Most of it will stay intact as the molecule or as the reactant. Now, these are double arrows, they're equilibrium arrows. What this means is they disassociate and recombine at the same rate. It's an equilibrium. So for every one H that comes off, another H comes back on. So the rate does not change here. It will keep doing this. And if you look at this picture over here, so this is also placed into a solution. In the light bulb electrodes are placed in the solution. That's allowing the light bulb to be very dim. And the protons that have disassociated will be attracted to the opposite charge electrodes, and that's what will allow this to light very, very dimly though. And these arrows are a huge indicator that this is a weak electrolyte. Always, if you see these arrows and you're talking about electrolytes, this is a weak electrolyte. One arrow going one way is a strong electrolyte. But what if you don't have anything? So in this case, the light bulb does not glow. Nothing's happening. There's no electrical current happening in here. Why? Well, let's take a look at this compound here. This is methanol. Methanol dissolves in water, very polar. However, it dissolves intact. The OH bond on it allows itself to interact with the very polar the OH bond on water. So it does dissolve. It's one layer, but nothing happens because it's not ionic. It has to be an ionic compound, or it has to be, in this case, some ions have to partially come off in order for a charge to happen, to be even considered a weak electrolyte. So this is considered a non-electrolyte. It will still dissolve. There's still one phase, but it does not dissolve. It does not conduct an electric current. So you can see here's a breakdown what a strong electrolyte does in solution, what type of particles, only ions, and then conducts electricity, and it gives you some examples. Second one is weak electrolytes, disassociates partially, mostly molecules and a few ions, very weak, and it gives you an idea. Acetic acid, I told you right here, there it is. And then the non-electrolytes, no dissociation, only molecules, does not conduct electricity, and it has a lot of carbons and hydrogens, and that's kind of a giveaway. You can kind of see that that's what involves non-electrolytes. Okay, so let's break down, give some examples of what we're looking at here. So complete each for a strong electrolyte. So now we're looking at dissociation. So we have calcium chloride, and it's a solid ionic compound. It will dissociate in water. What do we expect to happen? So which of these do we expect? Do we expect A? No, because it's going to dissociate. It will no longer be in solid. It will be in an aqueous solution. So these parts are right, but now it has to be balanced, even with charges. So it's easier if I show you what it is and then discuss how to break this down. So when you're trying to dissociate a compound, put a line if you can, and mentally see a line that allows you to know where you're going to cut this off. And then crisscross back up. And that will tell you what charge is going to go with what. Now you're not done, because you can put the 2 back and you get the 2 here. But when you do the 1 here, because that's, it's not showing, but there's a 1 here. If you put a 1 up here, it's not balanced, because you still need 2 of them to show for this 2. So you have to make sure you put a 2 in front. Charge never changes, because that's what belongs with this chloride, but you have to put 2 of them in order to balance the whole thing. All right, so here we have potassium phosphate. Now a line's going to go between the phosphate here and the potassium. So you're going to crisscross back up. So phosphate's going to have a 3, potassium's going to have a 1. So B is immediately out, but it has 1 charge, but we need to accommodate for the coefficient in front, and this would never work because we never mess with subscripts ever. So in this case, you're going to have to put a 3 to balance out. This means there's 3 potassium ions for the phosphate that has a 3- charge. Okay, which of the following reactions represents the dissociation of a strong electrolyte in water? I can tell you right now, I can knock a couple of these off very easily, because we want an ionic compound. We do not want molecules. Molecules are not strong electrolytes, so we can kick 4 of them off right away. 3 of them, sorry. 3 of them off. This is a gas. We want an ionic compound. Ionic compounds are solids at room temperature. This one's out. This is a molecule. We do not want it, and it's also a liquid. This is a solid. This is what we're looking for. Something that's a solid that is an ionic compound. And D, same thing as B. Liquid, molecular compound. Not interested. So if that, just knowing certain things like that saves you time and not trying to individually break one down. If you understand what goes with a strong electrolyte. Ionic compound. Ionic compounds are solids at room temperature. And this is the one that's going to break down. And then how do you break it down? We'll put a line where it's going to split. And then crisscross. We know that the 2 will go here, the 1 will go here. So this one's probably going to be fine, but you need to add a 2 for the 2 that shows on this side, and then it's balanced. Okay, write the equation for the formation of a solution for each of the following. The dissociation of potassium chromate, a strong electrolyte in water. I think that's chromate. I sometimes mess that up with dichromate. No, it's not dichromate. Forget what I said. Okay, so let's take a look at A first. It's easiest just to show you how to break it down so you can understand. Put a line where it needs to go. Take the charge out, because we know potassium doesn't have a 2+ charge, so that's got to go with the chromate. And now we're going to make sure that we adjust the coefficient in front of the potassium to adjust it all, and that's what we did. Now what about the partial dissociation of a weak electrolyte? Now, keywords: partial dissociation, not full, and weak electrolyte. We are going to have different arrows. We're going to have equilibrium arrows in this. So we need to figure out how that goes. And same thing, we're going to take this off, but you're only taking 1 off because it's a weak partial dissociation. It's not full. So only 1 proton's coming off of this. And that 1 proton is accounted for here, and the 2 here. So we still have 3 here. So this is a lot easier in a sense, even though it seems like it might be hard. There's really nothing to balance in front because we still have 3. We didn't lose one. We just kind of pulled 1 off. And it's still kept intact in aqueous. So keywords: partial dissociation and weak electrolyte. Even if you had just gotten 1 of those, that should have given you a hint that this is a weak electrolyte. And the last one, the dissolving of sugar, solid sugar in water. So this is only going to dissolve. There will not be any dissociation. And all we're going to do is change it from a solid into an aqueous solution. This does have to happen in order for it to be in solution. So that's what it's showing. one arrow going one way towards the products, but changing from a solid to an aqueous. Okay, now we're going to get into the equivalence of electrolytes. So we want to know how many electrolytes are in a solution. If you're going into the medical field, this is very important. What if somebody's dehydrated? They need something that, you don't want to overdo it, but you don't want to underdo it. So they, of course, they have, in a sense, a concentration value system in order to know this. So an equivalent, which is EQ, is the amount of an electrolyte or an ion that provides 1 mole of electric charge. So this is simply how I'm going to say it. Whatever the electric charge is on an ion, that's what it is per mole. And I'll show you an example. So in solution, the charge of positive ions is always balanced by the charge of negative ions. Of course it is, because you're dealing with ionic compounds and they are attached. So they have to dissolve. They will dissolve with cations and anions. The concentrations of electrolytes in intravenous fluids are expressed in milliequivalents per liter. And 1 equivalent is equal to 1,000 milliequivalents. Okay, so let's take a look at an example. So say you have a solution that contains 25 milliequivalents per liter of sodium ion. And you also have 4 milliequivalents per liter of potassium. You want to know how many of the positive charges you have in the solution. And it's very simple. Add them together. So 25 plus 4 equals 29. So we have, in this solution, we have total of 29 milliequivalents per liter. Now, we also have to have it balanced, because if you look back here, it says in solution, the charge of positive ions is always balanced by the negative ions. So we need to know what do we have of an anion. And in this case, it's chloride. And we must have it equal. So the total is 29 milliequivalents. We only have chloride for the solution. It's going to equal 29 milliequivalents per liter. Has to balance out. So let me show you how, because we're going to do a problem on here, and you need to understand how the conversion works. This is very simple. Don't try to overanalyze it. We've already gotten accustomed to seeing the ions. Now all you're going to see is an ion, and tell yourself that's per mole. What I mean, I have sodium, which means I have 1 positive charge per mole, 1 equiv per mole. So whatever the charge is, add the word equiv, and then tell yourself it's per mole. That's a conversion. Why? Because it can get really confusing over something that doesn't need to be that confusing. Since you guys have already made it this far, you do not need to. This is very straightforward and simple. And sometimes simple confuses people. Don't let it happen to you. Let's take a harder one. We have iron with the 3+ charge. So what's this mean? Take a look at the charge. Instead of saying 3 mole, you have 3 equiv per mole. Over here we have calcium. We have 2 equiv per 1 mole. Magnesium, 2 equiv per 1 mole. And the same thing goes for the bottom ones here. We have phosphate, 3 equiv per 1 mole. It doesn't matter if it's a cation or anion. Whatever that charge is, now it's an equiv and it's per mole. And I want you to understand that, because when we do a problem on here, I want you to see where that came from. So how many moles? Oh, let me jump ahead. Jump back. The laboratory tests for a patient indicate a blood calcium level of 8.8 milliequiv per liter. How many moles of calcium ion are in 0.50 liters of blood? This is not a difficult problem. You've done most of these dimensional analysis already. You are just being asked to understand a couple more conversions, and that is it. And they're not difficult conversions, because they're still matching something like kilo. So if you had to go from kilo to grams, it's 1 equals 1,000. So even the conversions aren't really changing. But let's take a look at what we have. So we're given with 0.50 liters. That's what we're going to start out with. And then we're also given the blood calcium level, which is 8.8 milliequivs per liter. We need moles of calcium, because that's what the problem is asking for, calcium ion. And then we need to connect using what we just covered as equivs. Calcium, here we go, has a 2 charge. That means it's 2 equivs per calcium, 1 mole. And then we use the conversion. So here are all your conversion factors and inequalities. 1 mole of calcium ion equals 2 equivs. That means 1 mole. See how we can set that up? That's what I was trying to point out to. Whatever the charge is means it's 2 equivs per 1 mole. And then we have 1 liter of solution with an 8.8 milliequivalents of calcium ion. We can set that up, and then we have our conversion. So now let's set the problem up. We take what we're given to start with, and if you get lost, units will always save you. If you do this right, you will always end up with the unit that you need for the final answer. So here we have liters, so we're going to start with liters at the bottom. Even if you didn't know, just look where units go. The units will lead you on that path. So now we have milliequivalents. So what are we going to do with milliequivalents? Well, you could have done 2 things. Well, actually, no. You want to get this out of milliequivalents. So you're going to use the conversion, and these are exact. These are exact, so we're not involving them. The only one that's not is the purple. And then we cancel out that. We end up with 1 equivalent calcium, but we have a conversion of 2 equivalent calcium ion per 1 mole, and that gets us to 0.0022 mole of calcium ion. So this is not difficult. You just have to learn the new conversions, and then you will see the problem before you even complete it. The laboratory test for a patient, so this is the same problem, but in B, if the chloride ion is the only other ion present, what is its concentration in milliequivalents per liter? Well, remember, if we go back, in solution, the charge of the positive ions is always balanced by the charge of the negative ions. So we must have something that's equivalent to 8.8. Oops, I jumped way ahead. And it does. So we will say that if the concentration of calcium ion is 8.8 milliequivalents per liter, then the concentration of chloride ion, the chloride ion, must be 8.8 milliequivalents per liter to balance the charge. And so it is. We have to have it balanced because ionic compounds are ionic compounds because of the cation and the anion. We don't just make that disappear. Okay, so here's just something in chemistry. Something related to health about blood plasma. Typical concentration of electrolytes in blood plasma have a charge balance. The total number of positive charges is equal to the total number of negative, which is exactly what we've been discussing this whole time. Varies due to nutritional, electrolyte, and fluid needs of the patient. And here's just a chart that you can look over. The purpose, you have your cations, you have your anions, and the purpose here is what needs to be done, and gives you some numbers so you can go over this if you choose to. Okay, so let's do some problems. In 1 mole of iron 3+, there are how many equivs? Remember, I told you to look at the charge, add equiv. So in this case, you should have said 3 equivs per mole. And that's what would have been the conversion for this. This one's a little trickier, but I'm going to show you the math for it. In 2.5 moles of sulfate, there are, now look at the charge. The charge, do not get worried and caught up with the 2.5. Don't look at that. Look here. There is 2 charge, so that means there is 2 equivs per mole. That's nothing that's listed here, and it shouldn't be listed here because it would be wrong. That is our conversion, because unlike this one that's only representing 1 mole, this one's giving us something to work with, so we need to do dimensional analysis on this, but we have our conversion. So 2.5 mole of sulfate, we set up our conversion of the 2 equiv per mole, and this ends up with 5 equiv, and that's B. And then 3, an IV bottle contains sodium chloride. If sodium ion is 34 milliequivalents per liter, the chloride must be matching that. So 34 milliequivalents per liter. And that's it.